This microwave oven is a truly remarkable feat of engineering. The rapid heating that makes microwaves popular is made possible by power provided from this vacuum tube. Now, if you picture a vacuum tube at all, it's likely in a radio like this. Inevitably, tiny transistors and microchips replace clunky vacuum tubes, but it's too soon to relegate them to the museum. Microchips can't easily replace tubes for producing power, for example, in heating food. Now, a microwave contains three main components. A vacuum tube called a magnetron. It generates the energy that heats food. A waveguide hidden in the wall to direct that energy to the food, and a chamber to hold the food and safely contain the microwave radiation. In principle, a microwave oven heats no differently than any other type of heat transfer. At a molecular level, heat is a transfer of energy that results in increased motion of the molecules in a substance. Since we aren't quantum-sized, we observe this increase in motion as a rise in temperature. In a traditional oven or stove, we heat food by placing a pan on a burner or in the oven where the walls radiate heat, which cooks the outside of the food. The insides cook when heat transfers from the surface of the food to its interior. In contrast, energy from the magnetron penetrates into the food, which means the whole mass of the food can be cooked simultaneously. How does it do this? Well, our food is filled with water, which is positively charged at one end and negative at the other. To give these molecules more energy, we expose it to electromagnetic waves that emanate from the tube. By definition, the waves have the electrical and magnetic fields that change direction rapidly. For this oven, the direction of the fields change 2.45 billion times per second. Water will try to align with the radiation's electric field. The changing field rocks the water molecules back and forth rapidly, and molecular friction from this creates heat as the motion disrupts the hydrogen bonds between neighboring water molecules. Now, you can get an idea of the wavelength of the energy emitted from the magnetron using cheese. Now, you can see on here sections where the cheese is completely melted and other sections where it's completely unheated. The oven's metal walls only reflect waves of a length that fits inside the oven. This standing wave causes hot and cold spots inside the oven. The three-dimensional pattern of waves is difficult to predict, but the principle can be seen by looking at the waves in a single dimension. The peaks and valleys in the wave represent the greatest energy of the wave. Well, the nodes here correspond to the cold spots inside the chamber. If I measure the distance between melted cheese spots, I find about 2.5 inches. That would be half the wavelength, the distance between nodes, and is pretty close to the actual wavelength of microwave radiation used. Using that wavelength, I can estimate the microwave radiation's frequency. The frequency is related to the wavelength by the speed of light. I get an answer that only has a 4 or 5% error, not bad for this primitive measurement. Now, the real engineering in the microwave oven lies in creating the magnetron that generates high-powered radio waves. It's truly an amazing and revolutionary device. The vacuum tube is inside here. These are cooling fins, thin pieces of metal that dissipate the heat as the magnetron operates. The key parts are these two magnets and the vacuum tube. Now, I have another one so you can see the inside. You apply a large voltage across both the inner filament and the circular copper outside. This voltage boils electrons off the center filament and they fly toward the circular copper section. The filament is made from tungsten and thorium. Tungsten because it can withstand high temperatures, and thorium because it's a good source of electrons. The magnets bend these electrons so that they swing back toward the center filament. We adjust the magnetic strength so that the now orbiting electrons just brush past the opening of these cavities. Like blowing over a half-filled pop bottle to make it whistle, this creates an oscillating wave, the microwave radiation that heats food. It's simply astonishing that these cavities can be made with high precision, low cost, and incredibly high reliability. I'm Bill Hammack, the engineer.